If you can grow tomatoes in a sealed space system, you can grow them without soil at home. The limitation is not your plant, it's the environment you put it in. Soil holds water unevenly, traps roots, and creates instability. But when you remove dirt and give your plant a controlled root zone, growth becomes faster, cleaner, and far more predictable. Today, you are building a $5 NASA-style tomato hack that replaces soil with a zero-dirt survival system. Traditional container gardening introduces immediate structural instability. Over time, watering cycles cause the dirt to settle and condense, creating a dense physical problem known as particulate compaction. This diagram shows the fluid dynamics inside that compacted pot. Water molecules follow the path of least resistance, channeling down unpredictable routes. This leaves distinct impenetrable dry pockets, while excess liquid continues straight to the bottom. That bottom layer becomes a stagnant, saturated dead zone. Roots trapped in this pooling water decay and suffocate from a lack of oxygen. Because soil introduces these chaotic variables, the plant is forced into a reactive state. It expends its energy adapting to a fluctuating environment, rather than optimizing for fruit production. There is a specific mechanical cost to this density. When aggressive root expansion meets a compacted barrier, the root tip physically bends, thickens, and struggles to push forward. This struggle consumes significant resources. The plant redirects metabolic energy downward, fighting physical resistance in the root zone, instead of driving upward growth. Stunted growth in a container is the result of a systemic limitation. The plant's biological potential is restricted by a medium that physically prevents it from reaching maturity. Maximizing growth requires abandoning the chaotic medium entirely and engineering the root zone from first principles. Solutions can be found in extreme environments. In an orbital system, the goal is producing fresh, nutrient-dense biomass without natural resources. The science of achieving this relies on the biological requirements of a root hair. For a plant to thrive, that root hair needs precise, simultaneous access to water and oxygen. In soil, water and oxygen constantly displace each other. When you water the plant, oxygen is pushed out. As it dries, oxygen returns, but moisture vanishes. The balance is always fluctuating. Static hydroponics solves this. It removes the variable medium completely, replacing it with unvarying, continuous inputs. The objective is straightforward: create a physical state where gas exchange and hydration occurs simultaneously. By eliminating the dirt, you stop managing agricultural problems and start engineering a predictable biological output. These exact physics apply to a $5 DIY build. The first requirement is an outer containment shell that is completely opaque. The solid exterior must physically block and deflect incoming yellow light waves, keeping the internal reservoir pitch black. If light breaches this wall, rapid algal blooms will expand in the water supply and consume the available oxygen. Once secured, we insert a net cup holding an inert medium like clay pebbles. Their role is purely structural support to hold the stem upright. They provide no nutrition. When filling the reservoir, the water measurement is crucial. The fill line must stop just before it touches the bottom of the net cup. Every component of this setup is purposefully selected to isolate the plant and enforce an engineered internal equilibrium. This precise measurement creates the central engine of the system, the air gap. Inside this gap, rising moisture continuously interacts with atmospheric oxygen, creating a permanent, highly humid aerobic zone. This specific environment triggers a biological adaptation known as root dimorphism. The plant develops specialized air roots, thick structures covered in microscopic hairs designed to capture vapor and gas. Below these, water roots plunge straight into the liquid reservoir to handle nutrient uptake. This air gap resolves the biological paradox. The plant is able to maximize hydration and respiration simultaneously, without the risk of suffocation. Unlike a potted plant where the root zone is hidden, this system provides immediate, readable metrics on its operational state. The primary metric is root morphology. Bright white roots confirm that the plant is achieving successful aerobic respiration. If those roots turn brown and soft, you are looking at the physical destruction of an oxygen crash, known as hypoxia. There is also an olfactory metric. A foul smell from the reservoir confirms that anaerobic microbial respiration has taken over. The upper canopy provides immediate feedback through turgor pressure. Upright, firm leaves indicate the system is successfully hydrating the plant. Because the system is transparent in its feedback, managing the plant becomes an exercise in reading predictable data rather than guessing. Once a mature plant reaches this steady-state dynamic, it requires no adjustment to erratic variables. It only requires simple replenishment. This precise environmental determinism allows for systemic scalability, completely decoupled from geographic constraints. Because the setup relies entirely on predictable fluid dynamics, the success of a single bucket can be cloned perfectly across industrial arrays. Agricultural efficiency is achieved by removing randomness from the equation. When you remove soil, you remove the biggest source of instability. Once the root zone is controlled, everything above it becomes easier to manage. A simple container can outperform traditional methods when the system is built correctly. Keep refining your setup, keep it consistent, and let the plant respond to the environment you create. And subscribe to Unearth the History. By building this container, you are applying the fundamental mechanics of high-efficiency indoor farming at home.